Good evening, everyone. My name is Ravi Kumar. I'm from TechnipFMC, and I'll be presenting on brittle fracture assessment of existing equipment as per APF 579-1, fit for fitness service. Maybe this is the first technical presentation involving values and formulas, so bear with me. This is basically to identify the scenarios where brittle fracture occurs and how to mitigate them. Recently, we executed a revamp of ethylene projects commissioned in 1970s. In the simulation studies, we identified certain scenarios where the process temperatures would be below the MDMT or the minimum allowable temperatures of the materials used. That means it will lead to brittle fracture of the equipment, leading to a lot of fatalities. So we assessed all the affected equipment and piping as per this APF 579-1 and established that all those affected equipment are safe to use. So before going into a case study, let's quickly look into what brittle fracture is. Generally, at high temperatures, materials behave in a ductile manner. That is, they absorb a lot of energy, they elongate to a great extent before giving away to fracture. They give some warning to the operators, some time to take some preventive actions. The same materials, when subjected to low temperatures, they give away at very low stresses. They don't elongate much, and they fail without giving any warning, leading to fatalities. So if you see this tensile test specimens, the brittle fracture occurs without any deformation, the straight one, which happens in a very quick manner, whereas the ductile fractures occur with a cup and cone. That means a lot of deformation will happen, and we get some warning, so we can take some remedial actions in the time. So in industry, MDMT, the minimum metal design temperature or the lowest temperature that is possible for the system, is used for selecting materials. In short, for thumb rules, the carbon steels are used till minus 29 degrees centigrade, whereas impact tested carbon steels are used till minus 46 degrees centigrade. So in revamp projects, these 5 scenarios and many more should be critically reviewed, because these scenarios can lead to low temperature excursions below the MDMT or below the minimum allowable temperature of the materials used. So these low temperature excursions can be of very short durations, but still in those durations, if any stress occurred or repressurization is made, then the equipment may fail without any warning. So a critical assessment shall be made for the suitability of all the materials, all the components subjected to these scenarios. The fit for fitness service assessment as per this APF 579-1 is a multidisciplinary activity involving engineers from process, materials, inspection, mechanical, everyone, process safety, to determine whether an equipment with flaws or damages is safe to operate or not. So basically, it will give us a roadmap to decide whether to use the equipment as it is, or to alter it, or to repair, or to demolish it. So the assessments can be made in 3 levels, 1, 2, and 3. When first one being a very conservative approach or a quick screening method, which is based mostly on the available data. Then the second, level 2, is a detailed manual and Excel software calculations, where extensive inspection reports and some stress ratios to be established. And the level 3 is a most detailed and accurate one, wherein extensive inspection data and numerical methods like finite element analysis will be used. So when first level fails, we can go to the second, and if that, and we can go to level 3. So in general, this APF 579-1 provides guidelines for the assessment of materials in many damage mechanisms like creep damages, fatigue damages, damages due to fire accidents, general metal loss, fitting, and everything. And specifically, part 3 of this code deals with the brittle fracture assessment, which we did in one of our projects. This is one of the case study where we implemented this brittle fracture assessment. It's basically when a low temperature excursions occur due to the failure of utility reboiler control loop. So we all know utility reboilers are used to boil off the lighter components of the feed and obtain higher purity products. But in case if this utility boiler control loop fails, then the lighter components or the low temperature components will flow through the downstream of the control valve, leading to the exposure temperatures below the minimum allowable temperatures of the materials. So if you see this schematic figure, in normal operating conditions, the minimum design metal temperature was set at minus 46 degrees centigrade. And so impact tested carbon steel was selected. But in the event of upsets, that is when this reboiler control loop fails, the lighter components will flow through this downstream piping and the tube side of the exchanger, leading to a critical exposure temperature of minus 60 degrees centigrade. That means making this entire system vulnerable to fracture. So in HAZOP studies, this was identified as critical and a mitigation plan was sought. So the immediate solution was to upgrade this entire affected system with next metallurgy, that is stainless steels, which will clearly ease the operational concerns, but will lead to a lot of long procurement times and cost investments will be high. So we resorted to a brittle fracture assessment of all these materials, like materials of these pressure vessels, the piping elements, the tube sheets, everything as per the guidelines provided in this API 579-1, and established that this system is safe to use even at so below temperatures. Let's see how we did this one. So first one, as I said, the level 1 assessment need to be done, which is based on the quick information available. If we see here, MAT, minimum allowable temperature, because we selected carbon steel, minimum allowable temperature is minus 46 degrees centigrade. But from the HAZOP study, the critical exposure temperature was identified as minus 60, which is colder than the allowable temperature of the material. So brittle fracture is inevitable. So this assessment, level 1 assessment failed. Then we proceeded with level 2. So level 2 is, as I said, it's a very detailed calculations are involved. So we need, we had to collect a lot of data from the plant, like the operational history, like the original equipment manufacturing inspection records, the drawings, dimensional data, material information like the heat treatments, welding procedures, ND, everything. And if it is piping, we had to collect even the isometrics, including the type and location of supports and everything. So we collected them, we critically reviewed each and every document and estimated the stress ratios, or it's basically the coincident pressure temperature ratios, which are based on the available thicknesses or pressure temperature ratings. The API 5791, if you see the graph on the right hand side, it allows us to estimate a further temperature reduction based on the stress ratios. For example, if I get a stress ratio of 0.65, this API allows me to take a temperature reduction of 19 degrees centigrade below the minimum allowable temperature. That means the final MAT will be of minus 46 minus 19, that is minus 65. And when the stress ratio is 0.8, and it gives me a benefit of 11 degrees centigrade temperature reduction with a final minimum allowable temperature of minus 57. So in both the cases, the CET was minus 60. In the first case, the final MAT was colder than the CET, so it passes. That means we can straight away use the materials without any materials and equipment without any modifications. That's good to use. Whereas in the second case, the final MAT is warmer than the CET. That means brittle fracture is inevitable. It'll fail in brittle way. So here, either we can go with the next level, that is level 3, wherein we have to get a detailed inspection data and use numerical analysis. That means it will take a lot of time to model the entire equipment, the pipings, and everything. Or we can install instrumented systems like SIS for tight shut-off pressures. For example, if in this case, if it fails level 2 assessment, we could have placed in safety instrumented systems at these locations and prevent the limit the process conditions. So this kind of benefits are given in the APF 579-1. And this is a typical safe operating envelope which we developed for each and every identified systems. In short, if you see this orange color curve, which is normal operating curve, and the material selected was a impact tested carbon steel with a minimum allowable temperature of minus 50 degrees centigrade Fahrenheit. So this was sufficient for normal operating conditions. But in the upset conditions, the same minimum allowable temperature or critical exposure temperature will go to minus 64, which will lead to a brittle fracture. So here we did the assessment, brittle fracture assessment as per level 2 and established this yellow curve. So as long as the operating conditions are above this curve, it's safe to use the equipment as it is. And if it falls below this, then either we have to upgrade our materials if economics works out. Otherwise, we can limit the process conditions to avoid the brittle fracture assessment. So this way we helped our clients to use the same equipment with same metallurgy without any issues in a safe manner. Thank you.